Alright, hopefully you guys can hear me. I just recorded an entire video and realized I didn't have the sound going at the very end. So I figured I'd touch back on this problem that a lot of people seem to struggle with while we're in lecture. And it was covering, Dr. Bang basically wanted you guys to describe the active site in terms of hydrophobic, hydrophilic, charge negative, charge positive, based off seeing what functional groups were interacting with that active site. So I drew this kind of off memory, so I might have it off a little bit, but I think I have it good enough to cover the points that were trying to be addressed during that. So we're going to start with A, then we'll go to B, then we'll go to C. I'll try to make it as quick as I can. The last video is about 8 minutes, so we'll see where we get. So we'll start with A over here. I'm going to draw it a little bigger and expand on it. So I kind of drew it like that. And we'll go ahead and draw the active site right here. So what we're looking for right here is, let's look at the functional group that's here. So we have some sort of carbon chain, which we know right away carbon chains are nonpolar. So because this is nonpolar, it's going to be hydrophobic. And the reverse is also true. Polar would be hydrophilic. So here we have a hydrophobic molecule. So let's put hydrophobic. And in order for a hydrophobic molecule to interact with this active site must also be hydrophobic. So when you're talking about hydrophobic and hydrophilic, or philicity and phobicity, it's not like charges. So charges, your plus and minus will attract. Well, in terms of polarity, your polar is going to be attracted to polar. Nonpolar is going to be attracted to nonpolar. So hopefully that clears it up if anybody's confused on if it's opposites that attract or likes that attract. Just remember this right there. So here, and this also is not charged, meaning this also is not charged. Alright, so hopefully that clears up A. Let's go to B. I feel like B was the trickiest one that we had today, but after this, hopefully it is crystal clear. So we have our N's, our H's, and then we have a big old active site down here. Huge active site. Alright, so let's start with what we know. We have an amide here. Somebody asked in class if this nitrogen actually had a charge on it. I guess they were seeing something in chemistry class or something along those lines. This nitrogen actually has a satisfied octet shell, or valence electron shell, whatever you want to call it. It has, don't forget, there's a lone pair of electrons. We'll draw them right there. It has 8 valence electrons, therefore it's a neutral. It has 2 hydrogens. So basically it's not charged as far as like a maybe a minus or a positive, but it does have a partial negative, and these have partial positives. And that's because nitrogen is electronegative, much more electronegative than these hydrogens. So these electrons in this bond are going to be close to here, just like how you guys are drawing. So we have partial positive hydrogens are somehow attracted to this active site. Now remember, this is polar, and over here we said polar is going to be attracted to polar. So now we know this active site is polar. Okay, so it's polar. Who cares, right? What's next? So in mentioning that it's polar, we're also mentioning that there's some sort of charge, like here or here. And we know that charges are attracted to opposites. So we have these partial positive hydrogens attracted to this unknown polar active site. Well, we know that it's going to be partial negative, and that's how those hydrogens are going to bond to that. Now, another good example that you guys did in your worksheet, it's a synonymous example, except it looks something like this. So draw your partial, oops, that's going to be a negative. Draw your partials, positive, positive. Okay, and then we have, this might look familiar. It's because it's a hydrogen bond. So draw your partials, and you can see in this hydrogen bond, we have a partial positive hooked to a partial minus. And I know some people were confused thinking that these should actually be partial positives over here. But if that was the case, you would actually see repulsion from the active site in the hydrogen. Because remember, like charges are going to deflect each other, or yeah, they're going to push each other away basically. Okay, so now let's go up to here, and we're going to do active site C. This R group can be anything. In this case, it's a carbon chain. And this was the active group, a lot smaller. Alright, so what do we have here? We have this is called a carboxylic acid, and it's very polar. So don't forget there's a C down here. Let me use a different color. There is a carbon down here, don't forget that. And what we're going to see here is this oxygen has lone pairs up here, and these electrons would be up here, and that's because oxygen has a partial negative, carbon has a partial positive. Once again, this would be an example of a polar covalent bond. And in order for this partial negative to interact with this active site, the active site needs to be positive, which is polar, which is hydrophilic. Alright, so earlier I wrote some steps to solve this. So step 1, recognize that the NH bond is polar. Once you understand it's a polar bond, step 2, what are the partial charges and how are those charges interacting with the active site? And for step 3, you conceptualize it and solve it. If the hydrogens are partial positive, then the active site must be partial negative. Boom, solve your answer. Also, a quick tip on the test. One of these answers, actually I think it was for this one here, the answers, so you had A, B, C, and D. A said something, B said something, C said something, and then D said something. It was like hydrophilic, something, 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 something. All of these ones said phobic, phobic, phobic. So here's a way where test taking skills can save you a lot of time, possibly a headache, so you can spend more time on the more involved questions. Right off the bat, you know this is polar, therefore it's hydrophilic. There's only one answer that's hydrophilic. So because there's only one answer that's hydrophilic, you know right off the bat that's the only correct answer. None of these could be right because it's not hydrophobic. So I'll zoom in on this. This was my other one I did. Let you look at that. If you want to look at this one, pause it, whatever. And then this is the one I just did with the sound. Hopefully it comes out good. And one last thing, because I know some people were struggling with understanding why there is partial positives and negatives. So I'm just going to do an oxygen hooked to a hydrogen. And then, so I'll do a hydrogen, and I'll have a single dot. Now this hydrogen can be anywhere. It can be anywhere in this circle. It's actually called the Heisenbug uncertainty principle, which explains how the electron is just it's just somewhere in space by chance. It's never in a solar system orbital how we usually draw. So when this hydrogen donates this electron to this bond, the electron is going to be over here, and the electron probability is going to be really high over there, and it's going to look something like that. And the oxygen's electron will be right there, and obviously it has these two. We'll draw another hydrogen. Very partial positive, okay? Or partial negative. But by pulling this electron way over here, the protons in this nucleus of this hydrogen are going to be a lot more exposed to this backside. And the electron is all the way over here where it can't offset this positive charge. And that's why you're going to get a partial positive back here, because that proton is a lot closer to, I guess we can say, the edge of the atom. It's a lot more de-shielded. Whereas this one is more shielded. And in future chemistry courses, you'll learn about the effects of shielding, de-shielding, and something called proton NMR, nuclear magnetic resonance, or something along those lines. But you'll get to that in a later time. So once again, here's that. If you want to pause it and take it for notes, whatever. Here's that. Let me know if you guys liked the video, because this took me less than 20 minutes to make, and maybe it's helpful to someone. Y'all take it easy. See you Thursday.